everybody, welcome back. For our next talk, we're really happy to have Miguel Mostafa, who's here from Penn State University. I already approve of his first slide, but he's informed me, because the title is not on it, that the title of this talk is HAWC.
Perfect, thank you. Oh, okay. So, first of all, thank you very much to the organizers. It's a great honor to be here, and also to be the only dude this morning. And also, I would like to apologize to the audience. I know that many of you came to see this young guy that they put in the pictures. I saw the picture. It's a more than a decade-old picture. I'm sorry if you came to see that guy. I wouldn't be offended if you want to walk out. It's my fault. I didn't say anything to Mauricio when he put it up. So, like Tim said, I'm going to give you a talk about the High-Altitude Water Cherenkov Observatory. So this is on behalf of the HAWC collaboration. They did all the work. We have the best students, the best postdocs, and that's what I'm going to show you. So my talk is dedicated to the people that had the bad taste of going to the dark matter, parallel sessions, and the cosmic ray stuff, and the neutrino stuff. So if you're in the gamma ray, you're not going to see anything new, but I'm going to give you a very, very brief introduction to the TeV gamma rays and to the ground array, and then I will show you my bias selection of what I think are the coolest, most recent results that we have, and then I will tell you what we're working on. So this, again, is a biased view. I cannot show you everything that we have because I only have 25 minutes. And if I got time, I'll tell you what we're going to do next. OK, so you saw a lot about Fermi. So Fermi is above the atmosphere, so they see the gamma rays directly. OK? And this is the beautiful sky of Fermi. And they work in the GeV energies. OK? These work in the low energies because of the size. You get a size this big, so you cannot reach the highest energies because the flux gets lower and lower. So then we go to the ground, and we have these beautiful telescopes that image the Cherenkov emission. When these photons go through the atmosphere, they produce the secondary particles, they produce Cherenkov light, and this is what they see. So they see indirect, they see the showers, okay? And they produce very beautiful images. They have excellent angular resolution, excellent energy resolution. And, you know, if you take the time, if you take, say, a decade or so, you can do a survey like this. Pun not intended. And then we have the ground arrays. So this is a picture of HAWC. It's a perfect complement of these two because we work in the high energy, we work in the TeV energy, multi-TeV energy. But we see a very big chunk of the sky, okay? So this is our sky compared with Fermi, and you just take a little piece, whatever piece you want of that, you see all that stuff all the time. And so, for example, that's the part of the galactic plane, okay? So a few words about HAWC. HAWC is in Mexico, so the thing that is important there is that it's at 14,000 feet in elevation, so it's pretty high. It's an array of 300 tanks. Each one of these, we call them detectors, but they are water tanks. Each one has roughly 200,000 liters of water, pure water, and the 300 cover an area of roughly 22,000 square meters, okay? So the important part is that it's an array, so it takes data all the time, rain or snow, 24/7, okay? So that's key, okay? And we have a huge field of view. Instead of having a few degrees, everything that comes from above, you just record it. So that's why you see a huge chunk of the sky, okay? We see 2/3 of the northern sky. All right, so this is the Fermi picture, and Marco this morning sent me the newest 3 FHEL, but they lower the energy. So this is every photon that Fermi sees above 50 GeV. Now they lowered to 10 GeV, but that has stuff all over the place, so that put us to shame, so I decided not to use the latest one. But so if you look at 50 GeV, this is a beautiful map, right? This is what I call the Fermi Smile. And so what we do is we look at TeV. So our energy range, and you can see the parallel between the two. So this is our field of view. We see these every day, and this is the integration of 2 years of data, okay? So that's what I mean by a huge field of view. We get everything in here every day. So the first thing that we do is we look at the crab, because it's the best source that we have in the sky. We see, like Francis said the other day, we stopped counting sigmas, right? So this is more than 100 sigma. We see 5 sigma on the crab every day. 6 hours the crab goes by, 5 sigma, okay? That's nice for the cosmic ray guys. 5 sigma source every day. Okay, so we measure the spectrum to see that what we're doing is fine. We do this in bins of size of the array. I'll get back to that later. And so this is our spectrum. People say, well, yeah, they kind of get the energy. We know that the energy resolution is not super great yet. I'll get back to that later. More importantly, from data now, we get our sensitivity curve. And why is that important? So this plot is tricky, and every time that someone else shows it, all the other experiments complain. They say, my hands are not that little, anyway. So the things that I want you to take from here is the sensitivity that Fermi has at GeV is the sensitivity that we have at TeVs, okay? So we're gonna do those maps at TeVs. That's what's great. And we don't do as well as we thought in the low energy. We don't reach the 100 GeV that we were promising, or, anyway. But we are doing much better than expected at 100 TeV. At the highest energies, we're doing much better than expected when now we have data. So this curve is not from simulation, this curve is from data, okay? And we are doing just as well as CTA thinks they will do at these energies. Maybe they'll do better than this. I wouldn't be surprised. But anyway, so there's no one else right now taking data here, okay? So those are the important points. All right, so the first thing that we do is we put all this together and we look at the map of the whole sky. So we look at the galaxy in our first year catalog. So that's like a year and a half of data. We have over 40 sources. This is like a blind search, and everything above 5 sigma we call a candidate source. And out of those 40, there's like a dozen unidentified, so new TeV hotspots. I'm not going to show you all the 40. I'm not going to show you all the 16 or so new sources, but just a few examples. These are right on top of 2 HAWC sources. These are the HAWC photon maps. I don't know if I'm allowed to show this, but anyway. So these are on top of these HAWC sources. And the nice thing is, like, the telescope like HAWC is again, the angular resolution is great, so we can use their information. They can tell us what is the size of the source, what you expect. Otherwise, it will be hard for us to tell them apart, especially in an area like this. So if you go look at the Fermi catalog, the Fermi map, there's a lot of different sources there. So for us, with our angular resolution, it's kind of hard to tell all these apart. So we're working on the morphology of this region. If we look over here now, we have these 3 candidate sources. One is right on top of a Veritas source, and there's very likely is this supernova remnant associated with this. And now we have, and Nahi this afternoon will show you, we do the spectrum together, Fermi, Veritas, and HAWC. It's beautiful. The other hotspots that we have in here, these are new, and we are studying this morphology too. We don't know if it's some contamination from the other source or not. This one here, Veritas look at this, and they don't see a point source, so they have a very strong limit on a point source. So if this is actually a source, it has to be extended. Otherwise, Veritas should have seen it. So they already rule out that this is a point source. And again, you will see this afternoon, so I'm not going to show you too much. If we look at this area, so this one is another one of these unidentified sources. This is the old map from Veritas. This has only like 36 hours. By now, they collected more than 60 hours on this source, so they confirm there is this source, and probably this pulsar-wheel nebula is associated with this hotspot. If we look at the Cygnus region, there will be another talk in the afternoon dedicated to this region. But if we look, for example, at J2006, right here, this is the Fermi map so this one in Fermi kind of show up in the 1 and then disappear in the 2 FHL and so on. And anyway, so they have clearly an excess. You can see the photons here on top of our contours. So we're working with Fermi on this. And there will be dedicated talks. So this is this afternoon. So Petra will show the galactic sources from HAWC, and then two talks, one from Nahi, which is not from HAWC, but she's working between the Veritas and Fermi observation of these sources. And then Michelle will show also the observations from Veritas and NuStar. You heard about NuStar this morning, of some of these sources. And like I said, Vinita will show this particular region later in the afternoon. The main point of this is like, I told you this is a blind search, okay? So we look at our excesses, and then we say, that doesn't mean that if your favorite source is not in this catalog, then we don't see it, okay? So for example, we're working with Katie. She has her favorite mixed morphology supernova remnants, and we are looking at those, then this is not a blind search, right? We're going to those spots and we say, do we see this source or not? Because maybe it was like 4.8 sigma, and that's why it doesn't show up in our blind search, right? But that's a mean. So if you have a favorite source and you want to work with us, come and talk to us, because even if we don't see it, having limits at TeV is very important. Okay, so let me move on from the catalog. Let's talk about transient searches. Like I said, we see all these sources every day. So each point here, this is the crab. So this is the flux on the crab as a function of time. And each point is 1 day, okay? So every day we see the crab, and this is the flux from the crab every day. We run this Bayesian analysis, and it says the crab seems to be pretty flat this year. So this is almost a year and a half of data. This is already published. And you can say, well, a day is kind of long. But you know, if you think about it, the predecessors, so Milagro, before us, these maps of transient sources were like 2 months. Each point was 2 months, okay? So an order of magnitude in sensitivity that we achieve with HAWC, it gives us this. Every day, we get this flux. So whatever happens, we can tell you that same day. So this is the 2-year map. Like I told you, if you collect the 2 years, this is an example of 1 day. Okay, so if 1 day you see this, you kind of see this guy. It's only 5 sigma, you know. If you squint, you know, that's the plane of the galaxy, maybe. And these are the 2 Markarians. Okay. So what you can do is you can start looking at this every day, right? So you run, for example, August 2015, and you say, you know, show me the map for every day. So every day you have a map. And then you say, oh, bleep, you know, so that day, that guy was bleeping, and you don't have to be pointing because you get all that sky, okay? So this is great for looking for these transients. No one has to tell you, you just look at your sky. So that's what we did, and this is Markarian for 21, and if you do the same analysis with these blocks, you'll see that this one is not consistent with something constant, and that's the August 2015 that I just showed you. We do the same with Markarian 501, and this is, again, in that same month, in 2 different days, the 2 of them were bleeping. So if you take one given day, so this is a typical day. This is not a typical day, so that's April 2016, and this was our first HAWC alert. So we're following these guys, and whenever they go above a certain threshold, we let everybody know. So this one was the first one that we produced, and now this is running smoothly normally. So we have these following particular objects, and then Tom in the afternoon will show you our real-time flare monitor, okay? So if you're more interested in that, you know where to go. Speaking of transients, we follow some GRBs. So we have a paper recently where we follow 64 GRBs from Swift and Fermi. This is the typical one. So this is the 3rd brightest GRB from the GBM, and the LAT saw it. So there's emission in the LAT energy range, and it happened very close to our zenith. So it's a great location for us to look. So that's why this is a typical one. So this is our limit. So we don't have any detection of all those 64, so we have limits on all of them. I'm not going to show you 64 limits. This is the nicest one. So this is the fluence that we see in HAWC, and this is the fluence that we see in GBM. The LATS is like less fluence for short GRBs than the GBM, and for long ones, it is something at the level of 10%, and that's exactly what we are doing too. We are at the same level. So before I move on to extended emissions, let me say a word about lower energy stuff. So these are the bins that I told you in size. So the smaller size, so this is like roughly 5% of the array got triggered. This is what we call bin 0. This is all data below a TeV, okay? And for that first data, this is what we see in the CRAB, and that's why we're not using it for the catalog, for the CRAB paper, and so on. And we have two excellent graduate students, one at Penn State and one at the University of New Mexico, working on this, and they are making a lot of progress. So this is after a lot of work. I'm not going to go into the details, but it is very promising that we will be able to recover soon this under the TeV data, okay? So if we do that, let's go back where we were before, we will be able to start working in this region below a TeV, okay? So that's very promising. So stay tuned for that part. So now let's move on to extended emission. So like you heard before, they mentioned that the positron excess could be due to nearby pulsars. So we see extended emission, and that's another feature of an array, that if the source is extended, so for example, Geminga, we see it with an extension of like 2 degrees, there's no problem for us, okay? It doesn't matter the size, we see in a big sky like this, so there's not a problem. So we see Geminga, and we see another pulsar very close by. The details I'll leave for Jim that in the afternoon. He will show you the details of this, and I'm not going to spoil the answer, so he will tell you if we leave room for dark matter or not for the positron excess. I can tell you that we already responded to the referee, so this is going to a journal that has, what's the name that I'm looking for? I can tell you, but I cannot talk to the dishonest media there in the back, okay? Because it's under embargo, but pretty soon it will come out, and Jim will tell you about it, okay? Speaking of extended emissions, so you can say, well, if I build a telescope with a larger field of view, so I will still see 2 degrees easily. Well, how about Fermi bubbles, okay? If you have to look at something that is this big, it's kind of hard. Instead, so these are the limits that we already published on the Fermi bubbles, at least the northern part, which is the one that we see from our side. Unfortunately, we don't get to see the whole thing. That would be nice. And these are the limits, okay? And then Hugo will have another talk on giant molecular clouds with HAWC, also in the afternoon. So let me make another comment about the way that we do the energy. Oh, I didn't look at you when you showed me the 10, sorry. The highest energy bin, what we call bin 9, is everything above 85% of the array. So any shower that triggers more than 85% of the array gets in that bin, okay? So we're trying to get a much better estimate than just the size, okay? So the proxy for now is, you tell me how big the shower is, I'll tell you what the energy is. It goes in that bin. So we have 2 students working on this. Unfortunately, you missed those talks already, but Kelly and Sam are sitting somewhere there in the back that I can't see because of the lights. One is at Penn State, one is at Michigan State. They're doing a great job. They're doing 2 different methods. I'm going to show you only one. Again, my personal bias. So we measure, for each shower, we measure the lateral distribution, okay? Like Ralph showed you yesterday, the difference is that now we have each point is 1 PMT, okay? So you could have up to 1,200 points in each curve. And we look for the place where we measure the signal the best, so the minimal uncertainties, and that came out to, for us, it's 40 meters, okay? So that's our ground parameter. Our ground parameter is the signal at 40 meters. And then you say the higher the signal, the higher the energy, okay? And this is 2 simulated showers. And don't get hung up on do you get it right or not. The two methods were very nice, and we get the energy right. But the main point here is the following. So if you look at 40 meters, this has 10 PEs. So this is log 10 of the charge in photoelectrons. So this is 10 PEs. But this one has more than 100 PEs, okay? Because we simulated like a 300 TeV photon, okay? The main point here is that right now, both of these showers are in this bin 9, okay? Because they trigger the whole array. So we can't tell them apart. They are in the same bin right now. So this is what these guys are doing. These guys are recovering the dynamic range in here. So this is data now, and this is a shower from the crab, and then you look at 40 meters, and then you say, oh, this is 1.7, so this is like 50 Ps. Oh, this is pretty interesting, right? So how do you know it comes from the crab? Well, this is the timing. So each one of these colors give you the timing, so you reconstruct where it's coming from. It's coming from the crab, straight. This is the signal, so you look at this, and it hits the PMTs like a photon. It must be a photon. There's no big charges, there's no muons outside here. So, and you look at the charge over here, and that's what gives you the 1.7 that I told you before. So what they did now then is this. This is bin 9, okay? And if you look, it goes, everything above 10 TeV or so falls into that bin, okay? So now, because they can measure the energy event by event, they can bin in energy and recover a quarter decade. So 10, 17, 32, 56, 100 TeV, 178. Okay, let's stop there. And now each one of these is a bin. And then you can say, well, I can do maps now for each one of these energies. Cool, even I can do maps. That's not hard, okay? The hard part is to do the spectrum now, because now we need to redo everything that was done over all these years for this bin 9, especially gamma hadron separation, especially the background, especially the angular resolution. You have to do it for each bin, because right now we are using the same values that we had for bin 9 that had all those energies inside, okay? So in fact, we're being super conservative. We are applying the cuts of 10 TeV to the 100 TeV showers. So there might be more 100 TeV photons in there that we're just cutting away, okay? So this is the sky at 56 TeV. This is the crab at 56 TeV, just in case you couldn't see it there. And if you look over here, this is the plane of the galaxy, and this is everything above 56 TeV. I know that you want to see 100, but you have to wait. Okay, so I need to speed up a little bit. One word about extragalactic isotropic emission. You heard a lot about the ice cube measurement, and then how Fermi gives you the gamma. There's nothing here. Look, this is 1 TeV, this is 100 TeV, okay? Who can measure this diffuse emission in this TeV range? That would be awesome, because then we can constrain even further what is the contribution from galactic neutrinos and extragalactic neutrinos. What is the origin? So we are working on putting the limit here to do it right. And now, before we had this bin 9 measurement, this was without completing the detector, with only 3 months of data. So now we have 2 years of the full array with bin energies, okay? So we're gonna do points in all these bins. So that's coming. I won't have time to do a lot, but I'll say a lot about Amon. It's close to my heart, so I had to mention it. We're putting HAWC data into Amon, so we want to do real-time correlation between high-energy photons and neutrinos. We want to do, obviously, gravitational waves. I think that is great. We know the astrophysical neutrinos, gravitational waves. To me, the next big step will be multi-messenger. When we start doing multi-messenger and we start finding the sources, multi-messenger will help us characterize these sources. Okay, so, oh yeah, that'd be nice, remember that. Okay. So if you don't apply any cuts and you take every shower that you get, these are all cosmic rays. So you buy one detector for gamma rays and you get a cosmic ray detector for free. There's a lot of work going on. We have a paper almost ready to be submitted about large scale anisotropy. There's no chance I'm going to make it, sorry. Almost done. Then we'll give a talk about the TeV cosmic ray sky that we see with HAWC. This paper will have the large scale as a function of energy, the morphology studies of this. We saw the small scale anisotropy too. We are doing the spectrum. This one is also ready to be submitted. This is the spectrum that we see in cosmic rays. We're working on separating light component from heavy component and so on. One word about dark matter. There will be 2 talks, one by Andrea on M31 and one by Tolga about the dwarf galaxies. The good thing of this is, again, if you want to study a very large area, you say, I want to study dark matter from a halo, something like this, like M31 that Andrea will show you, we can do it. We don't have a field of view limitation, okay? The same thing, if there's a new survey and they give you 20 new dwarf galaxies, you don't have to go and look at each one of them. I already have 5,000 hours in every point in the sky, so I just go and look, and I put limits on those 20 that day, okay? So that's the great thing of arrays. So I'm not going to say much more of this. Oh yeah, can it be nice to see the galactic center? Anyway, so I think I'm done. Oh no, okay. So this is the 3 FHL in the region of the galactic center. This is the field of view of HAWC. We just ran out of power right here. This is too inclined for us, and you can see how beautiful the correlation between GeV and TeV, and HES has seen this, and this is a Pevatron. So it will be really, really nice to have an array that looks at this region of the sky all the time, the peak of the exposure somewhere right here, and it will be the perfect complement for CTA, just saying. Okay, so we are building outriggers. I didn't have time to talk about this. This is the array that we've been taking data with, and we're going to put little tanks all over this area. Okay, I'm not going to ask you who's going to pay for it, so I know what you guys are going to say. But we already have the money, don't worry. It will be done between the end of the year and March 2018. This increases the effective area by a factor of 3 or 4, will give us higher sensitivity, so by a factor of 2 or more at the highest energies. This affects us at the above 10 TeV. So everything that I show you is going to get better. So quick show of hands, who wants to see the 100 TeV sky? Who wants to see the flux of this source at 100 TeV? Keep your hands up. Who wants to see the spectra of these sources? Who wants to see the extragalactic isotropic emission? Who wants to see the galactic diffuse emission that I didn't have time to show you as a function of galactic latitude? Okay, we need your help, okay? We need your help because we're a handful of groups in the US, and we're not getting all the funding that we need to support this handful of groups. So next time you guys see a proposal that says HAWC, you write freaking excellent, okay? Must fund. Even if you have no money to fund any proposal, you fund HAWC, okay? And we are pushing to build another detector in the south, higher, bigger, so we're looking for people interested in this. If you're rich, even better. We have nothing against poor people, but you know. All right, thank you very much for your attention. Thank you to the HAWC collaboration for the great work building this detector, operating and analyzing the data.
Great and entertaining talk. Do we have any questions? It's hard for me to see. So I do have one. In the, when we look at the ice cube neutrino background, what we find is that it seems to be isotropic or very close to it. And as you pointed out in the talk, HAWC provides a great bridge between Fermi-Lat observations of GeV energies and gives us a handle on understanding the ice cube neutrinos. Of course, for a ground-based mission, the more isotropic you get, the more cosmic ray contamination might become an issue. So what are the systematic limitations on a HAWC-like instrument for understanding the source of the ice cube neutrinos?
Good question. So this gets into the technical details of how the analysis is done. And the way the analysis is done is we look around sources. So let's say you take the crab, and you look at the place of the crab, and then you say, I applied my gamma hadron, but I expect cosmic rays to still pass that cut. There's still a lot of cosmic rays. So you're putting a lot of cosmic rays in there, which means that your limits are more conservative than they should. But there's a certain point, especially at the highest energies, that these events disappear. At 100 TeV, this background disappears. The signal to background is huge, okay? So the higher the energy, the cleaner the measurement. And I can tell you from the preliminary results that John has on this, it's beautiful. So the limitations are at the lower energies, we'll have a lot of cosmic rays, and that means that the limit will be conservative. So there's no way around that.
Any other questions? If not, let's thank Miguel again.